All right, so we are learning in section 11.2 about how you conduct a chi-square test on a problem where you have two variables rather than just one. And this is going to come up most frequently in problems involving two-way tables. So you guys will recall doing these back in chapter, it was I believe 1, way towards the beginning of the year, where we'd have two different variables going on and different frequencies for each of our groups. So we're going to learn how you can apply that concept of chi-square to a slightly new situation. So, our big problem for today is looking at a situation where essentially what's going on is at this restaurant, they're trying to play different kinds of music in the background, and they want to see if that has any sort of influence on what people actually order to eat in the restaurant. So, they've got either no music playing at all, they've got French music or Italian music, and they keep track of whether the people order the French entree, the Italian entree, or some other choice instead. So, looking at that problem, it becomes apparent pretty quickly there are two variables under study. There's what type of music am I actually going to play, and there's what type of food are the people going to actually order. Our explanatory in this problem is going to end up being the type of music being played. So we're trying to see if the type of music would explain or show us anything about our response variable, which is going to be the entree that people actually ordered. And both of these variables, type of music, French, Italian, none, entree, French, Italian, other, are categorical by nature. That's where the chi-square distribution is going to shine, is when you're dealing with categorical variables. And what's going to happen in this section is we're learning how two categorical variables are influenced by each other. This particular problem, it asks us whether we're dealing with an observational study or an experiment here. It does actually say that treatment was randomly assigned. And as just like a little throwback review question right here, that's exactly what you need to have in order for this to actually be an experiment. So this is an experiment because treatment was randomly assigned. It was imposed on subjects. So that is a nice little review of there. You just see if you had a condition or a variable being manipulated by your researchers, they chose the type of music that was going to be playing. It's not like they went to an existing restaurant and just like observed, oh, there's Italian music right now. They manipulated that variable for different groups of people. So we've already learned tools that we could use to analyze a problem like this back in chapter 1. It goes back to the idea of a conditional distribution, which was a concept back in chapter 1 that I said was kind of like sneaky difficult. It was that idea of breaking your data up into different piles and calculating percentages for each one. They ask us to calculate our conditional distribution of entrees ordered for each treatment. The way that this worked, again, just reminding you guys about really old stuff now. Figure out your explanatory. The type of music is explanatory. You want to break your data up into piles based on levels or values for your explanatory. So these are the three different groups for my explanatory. It could be no music, French music, Italian music. Each level of music gets its own little pile. And then I want to know, hey, out of the people who heard no music, what percent ordered French food? I would do 30 out of 84, and I would keep on dividing down the rows. I'm going to pause and just come back with percentages, and then I'll pause again and come back with an actual graph. All right, so I've got my percentages kind of sloppily written over there, breaking it down into each category of X. And then what I would do is I would make a graph to hopefully figure out and visualize what's going on so I can look for patterns. You can sort of see patterns if you just look at it right now, but a graph would be helpful too. So I'm going to make myself a little side-by-side or sideways bar graph here. Side-by-side bar graph, sorry. And I'm going to see if there's any difference between my little groups. All right, so here is my conditional distribution in graph form. Truthfully, these are a little bit annoying to make. It's tedious. I didn't enjoy myself while I was making this graph. but it is helpful in the sense that it allows your eye to catch things that maybe you wouldn't see when you were looking at just numbers. It doesn't super matter how you group things as long as you have everything labeled nicely. I chose to group by what the people chose to eat in little groups of 3 because I thought that would be a good way to draw out like what really felt important here. And when you look at the people who chose French food, the tallest bar is the dotted one, which is the people who listen to French music. In the Italian, this is so low right there in the middle for people who chose Italian food while they were listening to French music. But then the Italian music really shoots up for this one right here. Tons of people chose the Italian entree when there was Italian music playing. And it's harder to see if there's a major trend going on in the other group, but certainly in those first 2 groups, that's pretty noteworthy. So this next page asks us to make a graph, which we've already done, and also make a few sentences describing the distribution of entrees. That's sort of what I was talking about right here. I'm not going to actually write it out, but I'll just kind of talk out loud here. It appears that people were way more likely to choose the Italian entree when they actually were listening to Italian music. There was a 46.7%. Let's see, sorry, I might be picking the wrong number here. There was a 22.6%. I think I messed up my bars here. Oh, that's so sad. Let me see what I did. Chose Italian when you actually are listening. Oh, conditional distributions. Chose Italian and then listening to Italian music. Yeah, I've got this bar going too high. So this should have been like, I don't know, here-ish instead. Same principle still stands. So I could talk about this. If I did, I would make a few comments about specific percentages, such as saying, hey, the people who chose Italian entrees were more likely to do so when there was Italian music, mentioning percentages from the problem. So there's that, and that is fine. That is a review of chapter 1. It would be an adequate way to describe a problem like this. But what we're building towards here is actually the use of the chi-square distribution to help us in problems like this. Now, just like we talked about with goodness of fit, when we did just a one variable chi-square, there are too many options to try messing around with doing p problems. It's just too much. It's the same thing here. When we've got all these different groups and sublevels and stuff like that, the p-type problems that you would do a z-test on just aren't very effective. So what we need is a chi-square problem, not just for one variable like M&M color, but for 2 different variables, such as entree and music, that we can find a way to relate the 2 of those. And there are going to be 2 different tests we can run. This one in the video is called the chi-square test for homogeneity, or sometimes homogeneity. I've heard it said both ways. I say homogeneity. But this is going to be a test that allows us to look at 2 different categorical variables together and stop us from having to do the nastiness of all this. This was unpleasant on this slide. I didn't enjoy doing that. It's much better if I have a test that could get me a lot of the same information. So the hypotheses in a chi-square test for homogeneity are as follows right here. You're going to say for HO, remember that's always the statement of no difference. There's no difference in the distribution of whatever variable you're measuring. And this right here, when it's talking about the distribution of a categorical variable, they're referring to your response variable. So there's no difference in the distribution of your response variable for several populations or treatments. So this is going to come up right here, populations or treatments, especially big in experiments. In my experiment here, I had the type of music playing. So no matter what type of music was playing, HO would say, hey, there's no difference in what people are going to choose, no matter what music you're listening to. Okay? Seems like a reasonable null hypothesis. Then HA is going to say that there is a difference in the distribution of your categorical variable. So there is a difference in the distribution of entree choice for the type of group, depending on what type of music you were listening to. And we need a way to run a chi-square test on this 2 variable situation. So Finding the expected counts is a little more work here than it would have been back in goodness of fit 11.1 territory. So the way that this works, you kind of need a blank version of the table you were just working on. So I've got mine set up right here. In an AP question, you can just make your own little table on the side, and that's totally cool. But the rationale is when you go into this, HO says, hey, there's no difference in the music. The music does nothing. People are going to order what they order, and your treatment is not doing a thing. So the way you can kind of sort of think that through, altogether, I'm going to start with French food. Altogether, 99 people ordered French food. So if there were 99 people altogether, you would expect that to be evenly distributed between the people with no music, French music, and Italian music. So if all three of those group sizes were the same, I would just split that into thirds and go 33, 33, 33. But the issue is that the groups aren't always going to be the same. And in fact, there were less people who had the French music for whatever reason. So I can't just straight up split this in three. What I would do is I would calculate there were 99 people who ordered French food out of 243 people. So 99 out of 243, type this in a calculator real fast. That's about, I can't type, 99 out of 243 is about 40.7%. So 40.7% of all the people took French food, 99 out of 243. So that means if music doesn't matter, like HO says, I would expect 40.7% of the nuns right here out of these people to order French food. I'd expect 40.7% of these guys to order French food. I'd expect 40.7% of these guys to order French food. So I'm going to take my 99 out of 243, my 40.7%, and I'm going to multiply by how many are in each category. So when I do this, if I multiply this by 84, that's going to be like 34.22. Of course, I can't have decimal people, but that's what 40.7% of 84 is. And that's just going to be my expected group size. Decimals are okay, just like with goodness of it. Decimals are not only okay, they're expected. So I've got that going for me. Then what I would do for this next one right here, it's still going to be 40.7%. That was French food's overall popularity. But I would do 0.407 times 75 people. And that ends up being about 30.53. What ends up happening as you calculate these, I'm trying to walk you through why the percentages work the way that they do, but to get an individual box. So when I look at my top left box right here, what I ended up doing, if you see how I wrote this right here, you end up taking, even though it looks kind of weird to think about it this way, you take your row total, so 99, times your column total of 84, divided by the grand total. And that's how I got my answer for this first box. So that's going to be easier to remember and understand than probably calculating your percentages, taking percentages of group sizes and all that craziness. So for example, I'm going to jump down to a different random box. Say I want this box right here. I would take 31 times 84, and I would divide that by my grand total. 31 times 84 divided by 243. That is so messy. I'm going to pause and come back with a finished table. All right. So I went ahead and typed all of those in. Again, what you do is you take each row total and you're going to multiply your row total by the corresponding column total for each one. You take your row total times your column total, and you end up dividing that by your grand total. And that's how you're going to end up finding your expected counts for each of the different boxes. All right, so we know how to find an expected count now, and that's great. We're going to put it all together and learn how to turn this into our test statistic. The formula you guys see right here is the exact same thing we've been doing. Observe minus expected, you square it, you divide by expected, you add them up. That's all stuff you guys already know. The difference this time is that you don't just have like a couple options in a little row. You've got 9 different boxes right here. You have to take each matching pair in your boxes and do your formula with observed minus expected. So we would have 9 components going on in this problem right here. The degrees of freedom for a chi-square problem, you're going to take your categories minus 1, but you have to do that for each of your variables, and you actually multiply them together. So if you look, I would have 2 degrees of freedom based on my music and 2 based on my entree. I'm going to have 2 times 2, which is 4 degrees of freedom on this problem. So it's 4 degrees of freedom for my test statistic. So the final thing I would need to do here, I would need to calculate my degrees of freedom, which I already got is 4. That's just 2 times 2. And we have to actually calculate our little test statistic. So we have a nicer version of the table that I just slapped together up here. And then what we're going to do, I'm going to show one term and just come back with the answer. So in this problem, my top left numbers, if I just use those, I would end up, my observed is 30 minus my expected is 34.22. I would end up squaring that, and I would divide by the expected of 34.22. I would do the same thing with top middle, top right, etc., etc. And there's going to be 9 of these components in all. I'm going to come back with the answer. I don't expect you to write all of those out and do it, but that is how it would be done in theory. All right, coming back with the final answer here. If you actually calculate your test statistic and you do your little 9 terms all added up, it ends up being about 18.27. And then what I can do is I can turn that into my p-value on this problem by doing a good old chi-square CDF. So if you set that up with your lower of 18.27, your upper of large number, and then the degrees of freedom being 4, you can calculate a p-value. In the next video, we're going to build on this problem and learn how you actually take those pieces and make the appropriate conclusion for our test.